Yeah.
What is NIMT?
Numerical integral.
What is that?
That means that you do the integral and you get a number for your answer.
Oh.
Okay, this is the same thing as FNINT,
Oh,
like
okay.
FNINT,
You just plug it in.
NINT. It's the same. It's the Math 9. Yeah. Some, like a Casio calculator is not going to call it, it's not going to be Math 9 on a Casio. It's going to be something different.
Mm-hmm.
The different calculators have different, we use TI, so we use Math 9. It's not going to be that in other ones, so they're trying to be generic and call it, but it's a numerical integral. It means the result. Your calculator can do the value of an integral. It cannot tell you what the antiderivative is, right? Like you can't just do, what's the integral of x dx? It can't tell you that that's 1/2 x squared plus c. It can't do it. It needs numbers, it needs bounds, but it can give you the numerical value. It just can't give you the actual one. I kind of love the drama of this slide here. So like the publisher gives you some formatted base slides, and then I always just add them and manipulate them, add my own examples or whatever, but I love this one. They're like, the fundamental theorem of calculus is a triumph of mathematical discovery. I mean, it's like highly dramatic, over the top. Like, no, it was pretty big deal to know the fundamental theorem is that you can run derivatives backwards and forwards, okay, that there are both derivatives of functions and antiderivatives. So that key it did fundamentally change math from that point forward, but we're not quite so dramatic as all that. All right, the notation for an antiderivative is the capital of F. The fundamental theorem says that when you find the antiderivative, then you plug in the upper bound minus the lower bound. Okay, upper bound, so capital F with B plugged in minus capital F with A plugged in. Those represent the antiderivatives. I would like to see an in-between step. I'd always like you to show me what your f of x plus c is, and then your bounds going from A to B on that end, and then plug it in, okay? But please always show the antiderivative as part of your step, and then plug in your B and your A and subtract. And this works for every function that is continuous. It doesn't have to be differentiable. Again, I said yesterday, you can have corners, you can have cusps, you can have vertical tangents, but you just have to have continuity as well. There cannot be any asymptotes, there cannot be any jumps or gaps. This is how to evaluate an integral. So running an antiderivative is just doing the derivative process backwards. And so if we're running the derivative process backwards on 3x, the power increases to the number 3, and then we divide by the value of the new power. So that's the power rule backwards. The power rule forward is that you multiply and subtract 1. This one is add 1 and then divide. And then the antiderivative of the constant number 1 would be 1x. And then there's always a constant that is possible to make this a series of antiderivatives that have different y values, and then going from -1 to 3. Then we plug in our upper bound. We can reduce. So that'll give us 3 cubed plus 3. And then minus, and then we plug in our lower bound, -1 plus 1. So 27 plus 3 plus 1 plus 1, 32. And what that represents is the bounded area under this parabola above the x-axis. Okay, so between the function and the x-axis. Is that the one you were doing by yourself?
Yeah.
Did you get it right? Okay. Okay, let's do the next one. Oh, I don't know why I put that on there twice. Let's jump down to the sine graph. Okay, finding the antiderivative. So remember, the chain rule has to be accounted for. And so because this has the 2x, normally with the derivative of chain rule, we would multiply by 2. But because of the antiderivative for chain rule, we'll be dividing by 2. So the antiderivative of sine is negative cosine 2x. And then we have to remember to divide by 2. You can always check your work by retaking the derivative and applying the normal chain rule and seeing if it turns out to be the right thing. So you can always check. And then we'll be going from pi fourths to pi halves as our bounds. And so then at that point, then you can substitute your bounds. So we're at negative, I'll put my 1/2 out in front, the cosine of pi, and then minus the negative or plus 1/2 of the cosine of pi halves. The cosine of pi is -1. The cosine of pi halves is 0. And so the answer to this is positive 1/2, which again represents the area bounded under this sine curve between the bounds of pi fourths and pi halves. Yeah. Yep. Okay. Now we're going to have to pull out from our memories some of our rules for antiderivatives. Here's two situations where you're looking at a denominator, and they both have different antiderivatives. Okay. The first one has a denominator that's just 2x minus 1. That's a first degree denominator, right? It doesn't have any powers, doesn't have any squares, doesn't have any square roots or absolute values. It's simply 2x squared minus 1. Do you remember what the antiderivative is for a function that's in that form? It's an ln. Yeah, very good. But don't forget about the chain rule of the ln. And the other thing to remember about ln's is that their antiderivative has to be protected from being negative. So its antiderivative is always going to have the absolute value bars. So this is going to be the natural log of the absolute value of 2x minus 1. And then we're going to divide by the chain rule of 2. Add c, and then evaluate that on the bounds from 4 to 7. So that's going to give me the natural log of 13 over 2 minus the natural log of 7 over 2. There are some properties that say you can combine those natural logs if you want. So that would be the 1/2 of the natural log of the fraction 13 over 7. That would be a possible answer as well. The 13 and the 7 are subtracted for your natural logs, and then the 1/2 is accounts for the denominator. Be careful how you write it. Like, don't get sloppy and write natural log 13 over 2 like that, because that might look like the 2 is dividing the 13 when it's really not. So make sure you're clear that the 13 is part of the natural log and not to be divided by 2. So just be careful about how you write that. The bottom one is a different fraction. It's a different denominator. So that's another one you have to recognize who it's the derivative of. Like, all of these are going to have perfect antiderivatives. So you're not going to need U substitution yet. You're not going to need any fancy stuff, but all of these have perfect antiderivatives. What family does this belong to? Inverse trig. Which particular inverse trig is this one? Cosecant. Okay, this is the inverse, the antiderivative, or the derivative of the inverse cosecant. So its antiderivative is, the cosecant of x. So I don't need any chain rule for that one. Is there another possible antiderivative for that? What if you pull the negative 1 out to the front, and so then this was a positive 1. Would there be another different antiderivative that would work? You could say also the negative secant would also work. So if the negative was pulled out to the front, so it was a positive value, those are the same thing. Okay, cosecant and negative secant are the exact same. Plus C. Inverse secant, I'm sorry. Yes, on both of those. I wasn't writing those. So either, whatever you're more comfortable with. Do you feel like you're more comfortable with secant or cosecant? It's kind of up to you. Plus C. So I'm going to go back to the traditional. I'm going to say this is CSC inverse of X plus C going from 2 to 2 over rad 3. So the inverse cosecant of 2 over rad 3 minus the inverse cosecant of 2. And again, I am more comfortable with these fractions in their reciprocal form. I like rad 3 over 2 better than 2 over rad 3. And so then I can use the inverse sign, which is the complementary one to the inverse cosecant, which means I can do the same thing, and I'll be working with half. So just for me, I like those better. So then I'm looking for the unit circle radian positions that have a y value of rad 3 over 2. So that's going to be pi sixths. Nope, pi thirds. Then minus pi sixths. So the answer is pi sixths. All right, well, let's take a look at a couple exponentials. So remembering how to do an antiderivative assumes that you remember how to do a derivative. Okay, so if we were, let's just run that quick. If we were trying to find the derivative of 5 to the 3x, what would we do for the derivative? Besides start with it. Okay, then we need ln 5. And we'd need a 3. All right, so the antiderivative is just the division of those two things that you would need. And so our antiderivative here is going to be 5 to the 3x over 3 ln 5. So if you ever find yourself unsure, check what the derivative would say to do. And then typically you do the complete reverse of that. And you can always check your work by taking the derivative again to see if you had what you had was right. So this will be 5 to the 12th over 3 ln 5 minus 5 to the 3rd over 3 ln 5. There's no special rules for subtracting those. It's not like we can combine the powers or do anything. It certainly does not become 5 to the 9th. But I have seen students do that before. Okay, so it's not 12 minus 3 is 9. It's not 12 over 3 is 4. There is no, for powers, there's no special. The only thing I could do is a common denominator, and I could say 5 to the 12th, which is a really big number, minus 5 to the 3rd, and I could put them over 3 ln 5 like that, but that's about all I could do. All right, the antiderivative of an e is similar. It'll start as e to the half x, and then I will divide by half and Lenny, which, of course, Lenny is 1. So because Lenny is 1, and then because dividing by a half is the same as multiplying by the reciprocal, it's probably cleaner to write it as 2e rather than e over 1/2. And that would be 2e to the 7/2 minus 2e to the 1st. So again, you could factor a 2 out and have e to the 7/2 minus e, but there is no other subtraction you can do. You can't subtract the powers or do anything other simplification. That's really as far as you could go.